Okay, looks like we're good. All right, so we are approaching the end. Last time we went over kind of the additional architecture theory on top of basic computer architecture that is particularly relevant to microcontrollers. And that allowed us to kind of get a sense of what other considerations we have to make when designing such an embedded system, and how to work with the microcontroller itself. So all these will be kind of relevant as we walk through driver development. Some of them probably not today, but at the very minimum, we'll get going with hands-on for the programming tool chain. So that's why I've been stressing it so much. All right, so today we're going to finally get to the project. So before we do that formally, I wanted to talk about the general development process that we would use for microcontroller development. So I've been talking about this compiler toolchain the whole time, but there's a lot more than that that goes into actually bringing up a novel system. So the first thing, and this is what we've been talking about, is tool selection. So both the compiler toolchain, the programmer, and any other utilities necessary for your specific application, that's stuff that has to be considered way ahead of time. If you start picking out tools right as you are implementing the project, then basically you're going to run into time issues of trying to learn the tools as you're moving, and that gets to be a mess. So I wanted to list out the tools that we're using explicitly and then describe what exactly they do, because it's not exactly a one-to-one mapping with the compiler toolchain that I've been talking about. So for our specific purposes on the AdMega, we have a couple of open source tools that we're using to make development easier for us. So the first is AVR libc, and that should be installed in that package that I had you guys download. So it's basically a C library for supporting base level C functionality, and some utilities that are related specifically to the fact that we're running on the AdMega 328p. In general, AVR libc works on all AVR chips, but to go over it just slightly, so this link sends you to the library reference on the AVR libc page. So this lists all of the headers, the C headers that are available via this library. So all the stuff that isn't prefaced with AVR is like generic C utilities. So for instance, if we were working with time strings, this time.h would help you format those time strings very easily, as an example. But all the stuff that is prefaced with AVR is stuff that's specific to kind of chip development. And kind of the highest level header to include there is AVR io.h, which has basically all of the definitions for hardware that we're going to need to work with. So I guess it doesn't list it here, but it includes like definitions for memory mapping, pin number definitions, version information for the library, and that's basically all we need to interact with the chip as a programmer. There are definitely more. So if we have advanced functionality, like if we wanted to allocate interrupts, we'd include this header. If we wanted to do low power mode, we would include this header, and so on. So AVR libc just makes our lives easier so that we don't have to do everything by bare metal directly. AVR GCC is the compiler toolchain that I've been talking about. There are a lot of configuration options for it via command line, which are documented here. So the architecture macros configure AVR libc to know which kind of processor you're running. which is important for determining like which features your IC exposes specifically. So there's a command line argument for that. And this is specifically how that architecture command line argument listed MMCU expands. So you pass the MCU name, it exists under some AVR architecture version, and it expands to some macro that gets pound defined. So this page, which is this second link here, basically gives you all of the command line arguments that we could need to worry about. So if you guys have questions about specific flags, we can refer to this documentation later today. The other document that I point to here gives us ways in which the AVR GCC compiler organizes the low-level memory that it compiles into. So for instance, the C standard, like I've mentioned several times, doesn't really give strong definitions for the bit width of each of the variable types. So here, this documentation is explicitly laying out what those lengths are within the context of AVR GCC. So these lengths will not be identical to lengths defined with another compiler on another architecture. But they do apply for AVR GCC. So we can count on a character primitive type being 1 byte, and so on. So apparently ints are actually 2 bytes rather than 4 on this kind of processor. Likewise, there are deviations from the standard. So AVR GCC may support unorthodox behavior of the compiler. Yeah, so for instance, double and long double are only 32 bits rather than long double being 64-bit or beyond. And double, I think I mentioned, for most processors is 64-bit, but apparently not on AVR. I'm guessing that AVR doesn't have any support for 64-bit variables. But that kind of information generally is laid out in this document, which is the first link under AVR GCC here. And we'll get into like invoking this via the command line as well. AVR Dude is a program that's meant to interact with hardware programmer debuggers. So that dedicated piece of electronics that can upload code and actively debug your integrated circuit. AVR Dude talks to it, and AVR Dude lives on whatever host computer you're using for development. Let's see, and its command line arguments are available via the tutorial page. I think you guys have probably seen this when you're going through installation, possibly not though. So it's a command line argument, or it's a command line program, and all of its command line arguments are listed here. This tutorial just gives you kind of the defaults that you should usually use. And again, we'll just refer to it if you guys need it. Make is also known as GNU make. It's another command line program. Its purpose is mainly to take other command line programs with their arguments and make them repeatable so that you don't have to remember the commands. So whereas performing an entire build cycle takes like on the order of tens, and for larger projects on the order of hundreds of commands. And as programmers, we don't want to have to worry about that. So make operates on a make file that contains like a recipe, which describes how to call specific commands for a specific stage of your build process. So this will have like a batch of several commands that's kind of grouped together. There are 2 tutorials that I list here. This makefile tutorial, the first link, is a more in-depth explanation of what goes on in that makefile that you pass to make. The second one is kind of the very generic simplest implementation you could work with. I'm not really going to go through these because we're not going to walk through the make files in detail, but know that this program is just allowing us to operate several commands under the hood, and those commands are specifically to AVR GCC and AVR dude. I'll call these bare like once just to demonstrate how they work, and then refer to make for the rest of the build process. And then the last tool we're kind of going to be working with for our development environment is whatever text editor you guys want to use. So I use the Atom IDE just because it's super flexible. But you guys can technically use anything. You could use Notepad if you wanted to, or Nano if you're on a Unix machine. So visually, this process using these tools looks something like this. So we write our C source code in our text editor. We use AVR GCC to compile it into object files. AVR GCC as a suite also includes the linker. So we use it again to link any libraries that we need to bring into the system with those object files. And it doesn't technically produce a binary executable because this is an intermediate stage that we can then take and reconfigure before we send it to our target device. So ELF is a specific file format that includes both our valid binary machine code and some both debugging information and loading information for the programmer. So this AVR object copy is an internal command that's shipped with AVR GCC that takes that ELF format and spits it out into the raw binary machine code that'll live on our device in program memory. And then we take that hex file, as it's known, use AVR dude to communicate with the Arduino bootloader because it can talk to the Arduino bootloader in addition to regular hardware programmer debuggers. So AVR dude contacts the Arduino bootloader and makes sure this hex file can get into our program memory. So after we've picked our tools, the next step is to do board bring up. And this stage generally discusses, like if you have a novel printed circuit board that you want to work with, then that'll involve a lot of validating the electronics before you get to programming. So traditionally, you have several sub-circuits that each perform specific functions. You have to be able to provide power to your microcontroller and any other kind of subsystem that needs, more than your power supply provides. And that all takes debugging because fabrication, manufacturing cycles are almost never perfect, especially when it's your first iteration of developing this kind of printed circuit board. However, we don't really have to worry about that because we're using Arduino, which is a thoroughly debugged, off-the-shelf development system. So the fact that it exists as an open source product that the developers have already done all this electrical verification for means that we can skip that step entirely. There are still other parts of board bring up we have to do though. So half of board bring up is verifying the board itself, and the other half is verifying that it works with the tools that you've selected. So that we still have to do. Luckily, the tools that we've selected make that process pretty straightforward because we're running everything via command line. So we know which arguments we have to invoke. We know the expected behavior of each of our individual tools. And we have some confidence that it should work because these tools have been used for this kind of development environment for a while now. So the first thing to do really is the closest thing to your device in this process, which is AVR dude. So the first thing we will do is validate that your guys' install of AVR dude worked. So we'll just go through these instructions real quick. If you guys don't have the toolchain installed still, refer to this after you have it installed, basically. But I'll go through it once live for you guys.
Michael, we do have a question about using the Arduino IDE as a text editor.
Yeah, you can. I wouldn't recommend it because the Arduino IDE also like puts some restrictions on the organization of your project. Right now, I'd either recommend using a command line editor like Nano if you're on a Unix-based machine, or if you're on Windows, even just Notepad. Generally, I also recommend using something that has what's called syntax highlighting. So one of the reasons I like Atom a lot is because you can adapt different kinds of programming languages to be interpreted in different ways via syntax highlighting really easily. So I can do Control-Shift-L, and that'll show you like what language this file is being interpreted as, and so what syntax highlighting it'll be afforded. So Atom automatically recognizes this as a C file. Yeah, Visual Studio should be good. Both Visual Studio and Atom do apply kind of a higher level project in order to use their toolchain. But because we're not using their toolchain, it should probably be okay. So yeah, you can probably use it as a text editor, but just know that we should not be using Visual Studio's like build feature or debug feature for this project because we already have our dedicated toolchain. Let's see, where was I? So, right, so let's test our programmer to make sure that we can talk to our development board. So plug it in via USB. Take out my camera. And so the Arduino bootloader talks over a serial link over USB. So the machine that we're working on, your host PC, we need to identify which serial port the Arduino has been associated with. So I'm on a Windows machine, clearly. So I'm going to show you guys how to do it via Windows, but there's also a method of doing so via Mac and Linux. So Windows has this utility called Device Manager. And under ports, common LPT is listed all of the serial ports that are visible to Windows. So right now, the only port that I have exposed as a serial link is to the Arduino, and that's listed as serial port COM3. So I'm going to note that COM3 is the port that I'd like to target. So for Mac and Linux, because you guys are on a Unix system, there's this helpful command ls-usb. So if you run that via command line or terminal, then that should list all of the devices connected to your computer via USB connections. I don't know if Arduino will show up explicitly, but there should be something connected to TTYS and then a port number. Another way that could show up is like /bin/ser, and then it'll have a number. I think that's another format. But basically, you want to identify which serial device your computer is recognizing Arduino as. And if there are any issues doing so, please put it in the chat because this is important for the entire build process.
Wait, so how do we run the ls-usb thing on Mac?
Yeah, so I'm not intimately familiar with Mac, but there should be some kind of command line or terminal that you can open. So for Windows, that's CMD, opens this command line terminal that I can do things on. And Mac should have an equivalent. I don't know if any of you guys have used.
Should just be called terminal.
Yeah. And again, you should get something that looks like this. So it should give you like your current path and then a window where you can type commands. So So echo is a very commonly used command via the terminal. All right, and so once you're there, from anywhere, basically just type lsusb. If Mac doesn't have this command, I'm not quite sure what command to use, but we can look that up real quick.
Yeah, I just tried to run it and it said command not found.
Right, let me check that out real quick. Okay, so it looks like there is. Hold on a minute. Identify the ports on your Mac. Okay, I'm going to put this in chat. It looks like this is the command that we want. That's specifically for Mac.
Wait, what's the regular command?
lsusb. So that's right here. Actually, let me put that in the notes real quick if that didn't end up working. Let's see. Right there. Okay, so are you guys seeing this ls dev tty command? Is that working for you on Mac?
So if I get like, I ran that command and I get like a dev tty USB modem, is that the Arduino?
That, I believe so. If you don't have any other serial devices connected to your computer, then whatever shows up should be the Arduino.
Okay.
And we'll test it right now. So just keep in mind which port that exists on. So you'll need the full like TTYS and the port number. And again, for Windows, it's COM something. So for me, it was COM3. I have no idea what COM port it is on you guys' machine. Permission denied. So was that, Zoe, was that running ls dev tty? If you, yeah, you might want to run as a super user then. Oh, no, you need ls in front of that. Yeah. And again, for Windows, it's device manager. So device manager should give you this option for ports common LPT, and it should be listed as like the singular device if you don't have any other serial devices connected. So this is again for Windows, and for Mac and Linux, ls dev tty would be the command. Okay, so now that we know which COM port our device is on, we can actually invoke AVRDude to try and talk to our Arduino. So on Mac and Linux, this is again just another terminal command. So in that same terminal window, you can run this. In Windows, part of the quirks of using this tool chain is that we're going to have to rely on bash, which is a special command line shell. So instead of running cmd, like I've been showing you on Windows, part of the installation should have been git bash. So I'd recommend opening that up. And this, again, is just another kind of terminal. So from here, AVRDude should be visible. So if you just type AVRDude, then it should give you the help printout for both Windows and Mac and Linux. So if you type AVRDude and nothing shows up, then something's bad about your installation. It could be the path, or that you forgot to install AVRDude specifically. That I can't help debug right now because that installation takes longer than we have for today. So just trust me and follow along after the fact. So I guess just pay attention to the commands that I'm throwing in here. All of the instructions should be in these lecture notes, which also should already be up. So don't worry about missing anything. So we're basically just going to run this command though. So and the only thing that you have to modify about this command is this port denomination here. So whatever serial port that we've identified for our device, either COM or like TTYS something, that's what we put here. For me, that's COM3. And in sum, what each of these command line arguments is doing is saying, I'm going to call AVRDude, the program. I'm going to make sure it's using the Arduino programmer mode. So this flag specifically lets our AVRDude know that we're going to be talking to an Arduino bootloader. I'm going to use the verbose flag, so AVRDude will tell me everything that's going on. I've forgotten what the capital V flag is, but luckily I have the help printout. Do not verify. So I'm not going to be trying to validate that the program memory has been loaded with some image because we're not doing a load for this call. -P lets you know which processor you're using. So for us, that's the Atmega 328P. Oh, that command is wrong. That should be a capital P. Yeah, let me fix that in the notes as well. Yeah, so that that should be a capital P for port. So please change that when you're making this call. But the capital P lets you know which serial port you're talking to the programmer through. So for us, that's simply the serial port that our Arduino exists on. So, excuse me, that's what we found via device manager or via LSUSB or LSDevTTY. So put that port number here. And lastly, we have the baud rate. So this is the clock rate of the serial port. So that is how quickly we are sending new bytes of information. -D disables auto erase because we're doing a manual erase command, and that's what the E flag designates. So in sum, this total command will let us communicate with the Arduino bootloader in order to erase the program memory currently on the Arduino. And in doing so, this lets us verify that we can connect to the Arduino bootloader via AVRDude. So I'm going to run that command. And it ran pretty quickly. So it let us know that we're running a specific version of AVRDude. It let us know where the configuration file is that it uses to denote which programmers are available. And then it listed out all of the options that we're going to be running with. So for me, I'm running on serial port COM3. We're using the Arduino programmer and so on. So it did a quick read of the availability of different types of memory on our device. You guys don't need to know about these in particular, but the two that we're concerned with are EEPROM, which is our data memory, and Flash, which is our program memory. Yes, you do need Git Bash installed, and that should have been part of the installation. If you're on Windows, you need Git Bash installed. If you're on Mac, the standard terminal will do. In order to change directory, you would use CD. If you want to go up, you would do CD ... And if you want to go into a subfolder of your current directory, you would do CD and then the subfolder name. Zach, when you ran, so keep in mind COM has to be capitalized, first off. Are you on Windows? Because COM5 will be specific to Windows. Okay. If you're getting no feedback from ADVR due to git bash, that tells me there's something off about the installation. Unfortunately, we don't have the time to really get through debugging the installation issues. So probably just pay attention to what I'm doing then. Yeah. Okay, so we ran this command with the installation correctly set up. We can see that that AVR dude is able to read from our target's device memory. And we can verify that it also did the chip erase. So when AVR dude is functioning correctly, this is what you should see. There is the rest of the toolchain that we also have to validate, but that's not technically part of board bring up because it's not actually interacting with our hardware directly. Generally, there will also be more stuff here for if you're using a dedicated debugger. So a hardware programmer debugger also allows you to directly set program memory as well as inspect variables as your system is running. And unfortunately, due to the way the Arduino bootloader is set up, we can't actually use that debugging feature through the Arduino bootloader. We would need a dedicated hardware debugger that we could plug in separately. And I figured that's a pretty expensive piece of hardware, so we're just gonna not use a debugger for this project. It's pretty straightforward anyway, and we can validate each of the features just by directly programming the board. Generally, board bring up also extends into when you're actually writing the application, because a lot of times you are developing complex functionality that can't very easily be broken out on your printed circuit board. And so what goes on is the microcontroller is a necessary part of validating the rest of the electronics as well. And that can be kind of a back and forth between the electrical team and the embedded software team, at least in industry. If the project is small enough, then it's all you. So the next step is driver development. So drivers are pieces of software that are meant to interact with specific electrical subcircuits or dedicated hardware on your printed circuit board. And drivers could either interact with things that are on your computer's I/O bus, so the microcontroller I/O bus, and those would be internal electrical subcircuits to your microcontroller itself, or they interact with other hardware devices that are on your printed circuit board. So for instance, if you have, if one of your electrical subcircuits allows your microcontroller to communicate serially with another device, then you could have a driver for serial communication dedicated to that electrical subcircuit. But then you could also have another driver that uses that serial driver to communicate with a specific other kind of IC. So drivers nest, but generally when you're trying to communicate or control hardware directly, the software that does so is considered a driver. And these are fundamentally different from application logic. While they're still written in C, there's a bunch of different considerations you have to make when interacting with hardware directly than with writing pure C. The other fundamental difference is application logic doesn't touch hardware directly. It has to call other drivers to do so. But the drivers are dedicated to talking with hardware, so they work hand in hand. And we will get into driver development later today, actually. In industry, it's typical to break out all of the drivers into a library known as a hardware abstraction layer. And breaking that down, we're basically just trying to hide the complex hardware functionality behind a software interface that's easier to use. So the main purpose of this is, one, to create reusable hardware drivers, but also if you make your software interface generic enough, then it's possible to use the same interface across a bunch of different boards or across a bunch of different ICs. If the functionality, again, is similar enough. So oftentimes, like if you're working with the Atmel chip families, then Atmel will provide a library that they develop themselves for this purpose. So as a hardware abstraction layer, specifically Atmel's is called the ASF, or Atmel Software Framework, and they provide kind of drivers that run across a certain number of their chips. We're not necessarily going to do this because we're only developing our project for one specific chip. But know that in industry, it's very common to abstract things out into libraries to make the code reusable and potentially cross-platform. So that's driver development. And then the last thing, the last kind of piece of the hierarchy is the application logic. So the application logic sits on top of drivers, which sits on top of hardware. So the application logic is everything that isn't directly involved with interacting with hardware. And it describes the behavior of your programming target within the domain you're trying to develop. So for our project, that's everything that doesn't involve, again, writing our drivers. Most of the time, the application logic is domain specific. So you'll have logic that's dedicated to some feature that is specific to your project or to the field that you're developing your project in. So for some past projects I've worked on in aerospace, for instance, our application logic would include something like if you're doing satellite development, then our application logic would include how to communicate with other satellite subsystems, how to recover in the case of critical failure because you don't have a human there to reset the machine, and then what specific features you need for the mission. So all behavioral control code that just moves your system through some master state machine. And yeah, so the application logic typically follows a state machine just because you want your embedded system to be very predictable and have deterministic behavior. So that way, when you do board bring up, when you validate your application, you know that you won't have to revalidate as soon as you're in the field. And this state machine is typically the first part of the system that's actually designed with respect to software. And it's based on the end user requirements of the behavior of your system. For small applications, there may not be a distinction between application logic and drivers. And that's for, again, really small projects. I'm even breaking out drivers for the project that we're going to be writing, even though this project is pretty simple. It's not necessarily common to do so, though. I would highly recommend organizing your code in such a way that you break the drivers apart from your application logic, just as a means of debugging. And in order to develop your application logic, you can simulate hardware interfaces by like mocking a driver. So for, let's see, for something that we're about to get into, GPIO, or general purpose IO, if we wanted to write a driver for that, it'll have a certain set of functions that we choose to expose in C via some header. And in order to simulate a hardware interface, all we need to do is make sure that the C implementation of that driver is in fact a stub or something that doesn't actually talk to hardware, but behaves at the interface as if you have communicated with hardware. We're not going to do this because we're not I've already debugged the application logic and drivers for you. But there are certain software development techniques that can be useful in basically testing what you've written. The other kind of debugging that happens with your application logic is directly with a hardware debugger. So after you've programmed your device, you have your drivers written, you have your application logic running. If you're noticing some issue that you've diagnosed, so some electrical subcircuit isn't doing what it's supposed to do, even though you have written your code and you expect it to work, then it's very common to want to inspect the variables that are actually being set and cleared on your machine. And so you would use your hardware debugger to do so. Typically in industry, there's an order to development where you'll write your drivers after performing initial board bring up. You'll individually unit test those drivers as much as possible. So typically that'll be hardware in the loop. So you'll write some test image to your device that contains driver calls that exhaust its interface. So you'll cover every edge case of what the driver can do. And from there, you'll either use the programmer debugger to inspect what's going on at the programming interface for each of your hardware devices, or just run a pre-configured test and check the outputs of the device to make sure they're working. But as soon as you get to the application logic being complete, there are additional tests that you can run to validate performance. So in summary, the total development process can be summarized very shortly by this animation. And I'll wait for it to loop again. Actually, I can just refresh. So from the command line, we run a text editor. We create file led.c. We include avr.io.h. And within main, we write our hardware access commands. We save the file. We then make our program. So with a make file, we build it, and then we run avr-dude to upload that binary image. And instead of a hardware debugger, so hardware programmer debugger, so ISP, we're using the Arduino bootloader. There's also a dedicated tutorial for kind of getting a basic image on an AVR device that's written in pure C. That should look familiar. So this tutorial will walk you through the low-level steps and commands that are used when performing this development process. Because we're using makefiles, I avoid running these commands manually, but this tutorial should give you a much more in-depth look of what's going on at each stage of the development cycle, if you're interested. So I do have one demo project that we can run before we get into drivers. So that should be, it'll be available via the repository that contains the website, and I'll link you guys to that directly pretty soon. But basically, you can ignore these. Basically, the layout of the project looks like we have our main.c file. So this contains the entry point into our application source code. And then we have these two other C source files. We have a header that describes a test module that I've written that has two functions, configure port B and toggle port B. And when we look at the actual implementations for those, we include avr.io.h so that we have access to the hardware registers that we're using to do our programming. And I'll get into what that means. But we then access those registers directly for our functionality. I'm running through this because I just want to show you how the program upload works, and I'll get into what exactly these commands are doing again when we start talking about drivers. So I have a valid C file, and then also in this directory, I have a make file. This make file is pretty big, so I don't want to cover it exhaustively. But basically, the make file syntax is we have variables that we assign via equals. So I'm assigning the microcontroller name that we're using here. I'm assigning the frequency of the CPU that we're expecting, so the clock rate for our computer. The output format, so we're creating a hex file, specifically an Intel hex file, which is what that I designates. Our target is basically just the name of the binary file that we're going to produce. There's a dedicated directory for producing all of our object files. So when we compile our C files into that intermediate language, all of those object files will exist in this directory. This variable source will tell us which C files to include in the compilation stage. Oh, yeah, sorry. Here you go. That should be much easier to see. Unfortunately, I can't do that via the command line, so hopefully the video quality is good enough that you guys can still see that command line. This source, and also all of this code is going to be available. I'll link you to it pretty shortly. But I want to walk through one cycle of development first. So source just lists, it references variable target. So we have a main, this evaluates to whatever this variable contains. So we have a main.c that we're including for our C compilation. And then this command, this wildcard command, is just taking all of the other C files that exist in this directory the make file exists in, and saying also include those for compilation. There are a bunch of other variables that I'm not going to go over, but so we have this section of the make file is dedicated to defining all of the variables that will be involved in the compilation process. So these C flags are the command line arguments that we're going to pass to the compiler. I won't go into what all of them mean because most of them are not relevant to what we're talking about currently. We have some variables for dedicating command line arguments related to library inclusion, linker flags, so for that stage of compilation, and then our programmer options. And this is what you guys are going to have to modify if you want to run this. So we're using the Arduino programmer, and the AVRDude port is what we're going to have to modify. So for me, that's at COM3, but whatever serial port that you guys recognized, you'll have to modify this in the make file in order to build this. This command basically tells AVRDude to upload our target image, so that hex file, the binary machine code data, upload it with write permissions to Flash, which is our program memory segment. Here I list out the baud rate that we're going to use for communication. So these arguments, these variables should start looking very familiar because they're the very same commands that we passed to AVRDude via the command line. And this is where make becomes incredibly useful, is that you don't have to memorize any of these variables or any of these command line arguments anymore because you define them in your make file. So basically I did, I took all of our command line arguments that are necessary for programming and stuck them here. So those are all of the variables that we have to work with. The next kind of thing that a make file represents is called a recipe. Let's see, so let me scroll down to recipes. So a recipe is basically any identifier that is followed by a colon. And what this signifies is if you make a specific target, so let's say I say make all. I'm not going to run this because I'm not in the project directory right now. But if I make all, then it will attempt to run each of the targets that are listed here. So there should be a target called begin, and there is. And so so all, like what's after the colon is all the other targets that are necessary for all to succeed. And then everything underneath the target line. So begin is another target, for instance. And it doesn't target any other targets. So it instead is just a series of commands that we run together. So we're running an echo command with some message. But more relevant to us is build. So build lists all of the files that we want to produce. So this is just another target that's listing more targets to do on build. And the specific target we're interested in is this target.hex. So this will build a, this is saying that we want to produce a hex file. And below, there should be something that evaluates to .hex. This is another wildcard character that says, like, whatever our current target is, use that target name and then append .hex afterwards. So here we can see a dependency of targets. So we want to build a hex file, which requires us to have an elf file. And there should be another, there should be another target for our current target.elf. This requires us to have object files. So the object directory to exist. CC evaluates to our compiler that we're going to use. So this should evaluate to avr-gcc. And all C flags is just the collection of C flags that we provided up in our variables. So this is actually where our compiler command is being invoked, even if it's not evidently clear from this syntax. I won't go into specifics about the syntax, but know that the makefile is listing out the commands we need to do in order and according to the dependencies that we're trying to make. The gist of this file is that we want to expose specific targets to make when we invoke it via the command line. So if we call a naked make without a target, by default, it will make all. The other options that we have are make clean and make program. So make clean clears out all of the build artifacts. And to follow along with that, I'll show you exactly what that means. So I'm going to navigate into our project directory. I am going to open our terminal within that directory. So my path is within our project directory. I'm going to say make. So make will run all of the recipes necessary for compiling this. Ta-da. So if we scroll back up, I'll note that it's saying it's compiling main.c. So we can see the invocation of avr-gcc with all of its command line arguments that are passed in. Likewise, it also compiles this test module.c file, so the other source that we provided. It then links everything together in that ELF format. It then copies the program and data memories to sections within the hex file that are associated with those types of memory, and produces the hex file itself. So note that we have all of our object artifacts, so all of the intermediate format compiled files are listed in this object directory. And then we have a bunch of other build artifacts that we've produced. And I want to show you guys what exactly those mean. But before I do so, the rest of the commands, it produces this LSS file. So basically, we'll see that from the output in make, it'll show us how each of our build artifacts was produced. And then there are special targets within this make file that denote how big our file ends up being. And that's just for our own help. So we basically can't exceed the size of our program memory or data memory. And this information tells us how much or how close we are to exceeding it. So the build artifacts that we actually get are this main.hex, and that's what we'll be uploading to our target device. We have the ELF file that was used to produce the hex file. We have an EEP file, which is, so if the hex file is what's loaded into program memory, the EEP file is what's loaded into data memory. And for the program that I'm running, I'm not declaring global variables anywhere. So there's nothing that exists in data memory currently. It's all program memory. And that's reflected in this size report as well. So 0 bytes of data memory. And so this EEP file should be effectively empty. The other two files that I want to talk about are LSS and map. So the map file, let's open that with Notepad. The map file shows you where each of your variables is defined in memory. So it is a map of the memory that you've allocated with this, this build. So these named sections are different areas within memory that, yeah, they're just different areas within memory. So for instance, we have our data memory, which starts at address hex 008000100. And that's where all of our data memory should exist. Our text segment, that's program memory, and that starts at address 0. And there are a bunch of other memory segments that we don't have to worry about for this project. But if I scroll down, I should see definitions for our program. So let's see if I can find configure port B. There we go. So within the text section, that's again program memory, I have function configure port B living at address hex 80. So this, the map file is really useful for determining if a variable has been defined successfully, and if so, what its address should be. So if you're debugging like, why are my pointers not successfully setting a variable, you can make sure that your pointer contains the correct address for that variable, or if you're doing function pointers, that your function is at the address that you're expecting. This also shows you which functions have been optimized out, because if your function name doesn't appear in your map file, your function name has been optimized into code that's either part of some other function, or it didn't get compiled properly in the first place. So this is just, the map file is just another debugging tool that we have in our belt. I don't expect you guys to retain this specifically either, just know it exists. The last build artifact that I want to show you guys is the LSS file. And let me open that also with Notepad. The LSS file shows us the raw assembly that we use as our intermediate format. So this should be the equivalent assembly that's compiled for our program. All assembly files include section names. So again, this is just allocations of the memory areas that we're going to be working with. We have the data memory area, and we have the text memory area. So that's program memory. And this LSS file lists out kind of all the relevant information if we were writing this project in assembly. This also shows us how our code has been optimized, because these commands in assembly should be directly equivalent to the machine code instructions that are running on our machine. So within our program memory, that .text section, we have listings by address. So we have our interrupt vectors, which I think I mentioned prior, are just locations where the handlers to each interrupt live. So right now, they're all assigned this bad interrupt because we haven't actually assigned any interrupt service routines, and that's totally fine. We can scroll down until I hit, so we have our include AVR io.h. So this will show us our C codes side by side with the equivalent assembly instructions. So in program memory, it looks like configure port B is defined first. So at address hex 80, we have an LDI command, which is load indirect. We're loading value hex FF into register R34. So again, this is just the disassembly of what our valid C commands break down into. So this DDRB command that exists in test mod. So this configure port B is what we're looking at the disassembly of right now. So when we're assigning value hex FF into this construct DDRB, DDRB turns out to be a register, and that's register 24. And we're loading value hex FF into, I'm sorry, R24 is a intermediate register. Out is where we're actually writing to the DDRB register, and that's at memory address hex 04. Again, I don't expect you guys to retain this specifically, but know that the LSS file is a listing of the disassembly of your C source. That's also useful for debugging in some applications. So that's it for the build artifacts that I want to cover. So the only thing I had to do to make this using the make file that I provided is just run make. We could also run make build or make all, and that would equivalently do the same thing. The other thing we could do is, like I mentioned, make clean, which removes all of these build artifacts. So I'm going to do that real quick. And it deletes all the build artifacts. So the last thing we need to do is actually program our Arduino device. So once we have our build artifacts produced, we need to have this hex file in order to upload it to the machine. So we make first, and then I invoke this other command, make program. So program is a specific target that exists in our make file. And it requires our .hex file and our .eep file to exist. And the command we'll be running is the whatever variable AVRDude equates to. So that should just be literally AVRDude with its command line arguments. We're going to tell it to write our program memory, which is flash, and write our data memory, which is EEPROM. So make is just invoking AVRDude under the hood when we call this target make program. So when I do so, hey, we get our AVRDude printout with all of our command line arguments and our parameters listed, our memory inspected, and then it tells us that it's initialized so it can communicate with the bootloader. It's found the device signature, so the this is just like the ID of the integrated circuit we're communicating with, and we expect this to correlate with the ID of the Atmega 328P. It's parsed our main.hex file, and it writes it to program memory without issue. So this program that I've written just toggles an LED on the Arduino. So if I stop sharing real quick. Oh, well, I can't actually show this. Apologies. I ran out of USB ports to be able to plug in my camera. But rest assured, my Arduino's LED is blinking. Specifically, it's blinking at a rate of, at a frequency of a half second or on a period of 500 milliseconds. So let me give you guys the repository to be able to access this program code so that you can do this for yourselves. So I've uploaded all of this. So this AES microcontroller workshop repository includes both our project code, all the documentation references, and the lecture notes webpage. So this is another way of getting at all the documentation and notes. So you can find this repository, bring up the chat, right here. Oops, right there. This will take you to a GitHub page, which contains all of the source code that we're running with, and again, all of the other workshop resources. If you don't have Git installed, don't worry about it. Just download the code here. You can download a zip file. If you unzip it, then all of the projects that I'll be producing are in this projects directory. And what I just compiled and loaded onto my Arduino is in this projects 01 intro directory. So we have the makefile and all the source files. So I'm going to move on because we still have some driver information to get through. But if you follow the instructions that I've been doing on screen, then you should be able to reach the same intro project uploaded onto your Arduino. So you should see the LED blinking as soon as you do this. So yeah, I'm going to move on. I'll also include that link to the repository in the notes after today is done. It's not currently listed anywhere here. Okay, so now that we have validated our board and our tool's ability to connect to our board and a basic project on our board, we can now get into driver development. But to do so, we kind of need to know which drivers we'll actually need for this project. So I want to go over what exactly the project is that we'll be making as a brief introduction. So we're going to be making a simple MIDI controller. And for those who aren't familiar, MIDI is a digital standard for communication with devices intended to do music production. So in full, MIDI stands for the Music Instrument Digital Interface. And it's the set of standards that allow us to communicate with MIDI devices. So a MIDI controller specifically is a MIDI device that sends commands, like live commands, to other MIDI compatible systems. So synthesizers, mixers, sequencers, and other kinds of MIDI associated music production devices. The specific MIDI environment that we're going to be using is, I think I had you guys sign up for an account on Audio Tool. So Audio Tool is a digital audio workstation that simulates having synthesizers and mixers and sequencers and all the above. And it is luckily compatible with MIDI. So once we set up our MIDI interface on our host computer, we should be able to talk to Audio Tool via this MIDI controller. So we're going to be using our hardware device to send commands to our digital audio workstation. If you already have a DAW installed, if you like producing music, then this MIDI controller should also be able to talk to that. So as a note, our MIDI controller doesn't produce sound on its own. So we're not producing a synthesizer today or in this workshop. The MIDI controller only sends commands to devices, and those other devices are the ones that produce our sound. On our MIDI controller, we're going to have 4 buttons and an analog knob, which is really minimal for a MIDI controller, but that's all that came with our kit. And I've included a link to the kit here. So we have, apparently the kit has 5 buttons and 1 analog potentiometer. And that's what we'll be using to implement our MIDI controller controls. So to connect our MIDI controller to other systems, we need to support communicating MIDI messages, which are the MIDI compliant standards messages that are used to contain our commands. And while we could expose a MIDI connector, and I guess for those of you working on Mac, you'll likely have to do this unless the Python program works. We could choose to expose a hardware MIDI interface, but I've noticed that most machines nowadays don't actually have this MIDI port, and you guys likely don't have MIDI equipment unless you already do music production. So I've instead opted for simulating our MIDI connection over a serial interface. So specifically, we're going to be using the same serial interface that we use to program the Arduino. Luckily, the Arduino bootloader also allows us to communicate serial information to and from our target device after it's been programmed. So yeah, this our development paradigm will not use MIDI hardware interfaces. Rather, we will use the existing USB connection on our Arduino to send our MIDI messages. This does, however, mean that on the device that we connect to, so our host computer, we'll need to interpret the serial information as MIDI, and that's what the hairless serial to MIDI bridge is for that I had you guys download. And again, for the Mac users, apparently since hairless doesn't work on Mac, if you use that Python alternative option, which I will also add to the notes, that should be performing the same function. It should expose a virtual MIDI interface on your computer based on the serial connection we have to our Arduino, which is sending MIDI messages over serial. So the total functionality that we have to support for this project is we have to read button state to support our MIDI controller buttons. We have to read our analog potentiometer voltage to support our singular knob. We have to communicate serial data, and we optionally may have to keep time depending on if we want timed operations. I'm going to say we're not going to be supporting this just because we don't have a lot of time left within this workshop. But the Arduino does provide the hardware necessary for using timers. So the drivers that we develop should directly support these functions. There is another existing, there's a number of MIDI controllers that have already been developed on Arduino. So if you want a more powerful MIDI controller that isn't necessarily developed in C, here's an example of one. But you guys can reference that later. So we've finally gotten to driver development, which is the low level actually interfacing with our hardware. So before we could just upload pure C onto our target Arduino device, which is great, but it can't exactly do anything on its own. You can perform computations, but in order to get data into that computation, you need to be able to communicate with external devices that exist on the computer's I/O bus. So those electrical subcircuits that we want to target are known as peripherals. So a peripheral within a peripheral that's inside the integrated circuit that we're targeting. So the Atmega 328P peripherals that are supported out the box are listed in the datasheet. So let me go to page 15. So the internal peripherals that are endemic to our system are all attached to the I/O bus. So this block diagram lists the architecture of the integrated circuit. And note that inside this AVR CPU is the AVR architecture computer core that runs everything else in this system. We can note that it has connections to flash and SRAM. So SRAM is our active data memory when we're running programs, and flash is our program memory that our instructions are actually loaded from. The AVR CPU does all that work, and it connects directly to the I/O bus. So this giant block of peripherals here denotes all of the functionality that the Atmega 328P exposes for communicating with the outside world. So we have a couple timer counters, which do timing operations based on some clock signals. We have an analog to digital converter, which we'll be using for this project. We have USART, which is a serial interface, which we will be using for this project. And then we also have direct access to ports, which can be configured as general digital pins. So we can set pin state, read pin state, and in some cases use them as interrupt sources, which we will also be using for this project. So whenever I try to become familiar with a new chip, the block diagram is typically the first thing I try to find because it lists all of the functionality available. The next thing I try to find is a listing of all the specifications. So like max clock frequency and then the electrical parameters, which are also found in the datasheet. But for driver development, it's very helpful to know what you can target and what you'll have to support as an external peripheral. So some device that you plop down on your integrated circuit, or sorry, on your printed circuit board outside of the microcontroller chip. So peripherals are therefore denoted as either internal, so that's these hardware targets that exist within your microcontroller's integrated circuit, or external peripherals that you have to communicate with via the microcontroller's pins. For AVR specifically, and most microcontroller architectures, peripherals are given a programming interface via registers. So this I/O bus may connect to specific signal lines within each of these peripherals, and those signal lines may be driven from a register somewhere defined in your CPU. For our development for this chip specifically, and again, most integrated circuits, most microcontrollers, these registers are memory mapped, which means the registers aren't necessarily addressable as registers. They are instead addressable as memory addresses within our data memory. Or I think it's actually program memory that we address. So the peripheral registers, in order to access them, all we have to do is access a memory address like we would any other variable's pointer. It's also necessarily part of the physical RAM segment. So we write and read from it as if it were a variable effectively. And that's how our hardware devices are exposed to programmers. So that's our control interface for interfacing with hardware. And I've already shown you guys the complete listing. So now that we know what our programming interface is to control hardware, and we know which hardware the Atmega 328P supports directly. So we'll again be targeting our analog to digital converter, our serial peripheral, and then the port peripherals, which are digital pins. Now that we have a picture of what's supported, we know that we don't need any external peripherals. So we don't need to communicate with any external integrated circuits that provide functionality that isn't exposed here. So we can get straight to driver development. So for GPIO, general purpose IO is the concept of treating one of your IO pins that are at the edge of your integrated circuit. We're going to be treating them as purely digital signals. And the GPIO documentation is found on page 84. So this is also in the data sheet. We have a brief electrical schematic dictating how each of these pins behaves when it's configured as GPIO. So we have pin PXN. So X is the port that the pin is associated with, and that's just the collection of 8 pins that it's on. And we have N, which indicates the pin number for this pin. So for instance, the Arduino LED is connected to Mega 328P pin PB5, I believe. So each of these pins has these internal connections. So if this XN pin is exposed, at the edge of your integrated circuit. All of this is internal to the microcontroller's implementation. So this is the hardware that's actually connected to each pin internally. And I believe each of these are configurable. So we have a configurable high impedance, a configurable pull up, and then the pin has some capacitance to it. But that's not necessarily super useful information for our project right now, because all we need to do is support a button. Here is a logic diagram, which shows us internally via registers what we can configure about each individual port. Or each individual pin. You don't need to know exactly what's going on here because I'm going to go into the registers specifically. But when we're looking at a general purpose IO pin, generically, it can be configured as either an input or an output. So an output pin is something where we are driving the voltage level on the pin. So it can either be logic high or logic low, and that's something that our microcontroller is directly controlling. If our pin is configured as an input, that means our intention is for the microcontroller to read its voltage level. So there are two other states that we can apply when a pin is in input mode. We can either configure it to have an internal pull-up, which means internally we are setting this current path to be active. So we are configuring the normal logic level on this pin to be logic high. And in order to change that pin state, some external circuit would have to pull it low. So very likely that would mean connecting it to ground. So that's only when we have this internal pull-up configured. If we instead use the high impedance mode, the voltage level on this pin will follow whatever voltage level it's connected to in the external circuit. And again, because this is an input pin, we will be reading the pin state from our microcontroller. In order to support these functions, the Mega 328P exposes a couple of hardware registers that we can use. And these hardware registers are memory mapped. So the data direction register allows us to control whether or not a pin is configured as an input or output. If the bit corresponding to a pin is configured as, or is set, then the pin is configured as output. And if the bit is cleared, or 0, then it's configured as an input. The two other registers we have are the port register, which has different behavior if the pin is configured as an input or output, and the pin register. So the port register, if your pin is configured as an output pin, writing to the bit within the port register corresponding to your pin will set the logic level at the output. So if I write a 1 in bit index 0 of the port register for a specific port, then I would expect the pin associated with that bit to be set or logic high at the output on our integrated circuit. If our pin is instead configured as input, so if we have our DDR register bit set to 0 or cleared for the associated pin, if you then set a bit in port, you'll either configure it as a pull-up, or if you clear it, you set it in high impedance. Lastly is the pin register. If you read from the pin register for a certain bit, that'll indicate the current logic level on a pin, regardless of whatever the data direction register is configured as. If you write to the pin register, it'll toggle whatever state is currently configured in the port register. So for instance, if our pin is configured as an output pin and the port register has its current assigned logic level, if we set the bit in the pin register corresponding to that same pin, it will toggle the port register, and so it'll toggle the pin state. And this is really helpful for having a very quick instruction that will do this pin toggle. because the other way we could do a pin toggle is we could read its current state and then apply the bit level that's exactly the negation of the current level, which equates to basically two commands rather than one. If the pin register is read, then it'll give you the current logic level on the pin. And that's regardless of whether or not it's configured as an input or output. So these three registers in sum will let us control our individual I/O pins that the Mega 328P exposes. And we'll need this specifically for if we want to set the LED, then we'll need to configure the LED pin as an output and set its logic level. But at the same time, we're also looking to support buttons. So if we want to be able to read our button state, we need to configure those button pins as inputs. And when we get to the actual hardware layout on this project, I'll give you guys a schematic for how to hook up the buttons to the correct pins on the Arduino. So for now, I want to give a quick demo of GPIO functionality. So I have a new project. If you guys have downloaded the repository, then this will be located in the projects directory under 002 GPIO. So I have some new source files that I want to go over. So our application looks like we're including a driver file for GPIO functionality. I've noted that the Arduino LED is on pin B5, which equates to Arduino pin 13, I think. That's not necessary, but note that when we access pin B5, we will be able to set the LED state. And in order to show out the functionality of GPIO, I'm using an input pin to control the state of the LED. So we will be reading from Arduino pin, or at Mega 328 pin B4, which equates to Arduino's digital pin 12. So if you look at the Arduino, let's see if I have the documentation up. If you look at the Arduino, there's this pin 12 labeled. So if this is the pin header, if we connect one of our jumper cables that was included in the kit, so that's just one of those wires. If we connect that to pin 12 and the other end of that wire to our 5-volt pin, we'll be supplying 5 volts to pin 12, which is a logic high. So we'll be setting pin B4 to logic high. And this application is just setting the state of pin B5 to match the state of B4. So if we assign a logic level high, so 5 volts, if we plug that into our pin 12 here, our input pin will be logic high, and so the LED should match that voltage. And likewise, if we unplug the 5 volts and instead plug it into ground, that will be 0 volts or a logic level low, and then the LED would reflect that by turning off. So to support that, I have some driver functions that I've exposed. So I have set level, which under the hood is configuring the port register. And I have set direction, which is under the hood configuring the DDR register. The schematic. So the documentation I've been referencing is under that repository. So if you download the repository under docs, I have the pinout for Arduino. And that's the document I've been looking at and showing on screen. I haven't really provided a schematic for this demo because it's just connecting a wire between 5 volts and pin 12 or ground and pin 12.
And chances are, if you were to look up Arduino Uno schematic, you could find something fairly similar as well.
Yeah, I've just co-located all the documentation for you guys in this docs folder. So also in this folder is the schematic of how the Arduino connects to the Atmega 328P. And I think I've showed you guys this before. Actually, if we look for it, we could find PB5. Let's see. It should be connected to the LED. Maybe it is indirectly. Or is it PP4 that's connected to the LED? I don't actually remember. No, it is PP5. Somewhere in here, there should be a connection to our LED, but I am not seeing it. Well, I don't want to waste time trying to find it, so. Oh, a minute. Here it is. It's not shown directly, but this SCK net. So PB5 connects to the SCK net, and the SCK net connects to I don't know why I'm blanking, a buffer that drives this LED. So this is the Atmega 328P, and here's all of the surrounding hardware on the printed circuit board. So that's also in this documentation directory. But back to the code. So I've provided this, oh man, did I really? Dang it. I provided these functions that are part of the driver for GPIO functionality. So set level sets the pin level. So if you're in input mode, that configures it either as high impedance if you pass a logic true here, or I'm sorry, high impedance if you set logic false here, or a pull up for logic high. And in the case of output mode, this just sets the logic level on the pin. Likewise, set direction sets the pin direction as either input or output. And so we are configuring our LED pin as an output with its starting state as logic low. And we are configuring our input pin, so PB4 or Arduino digital pin 12. We are configuring that as an input, which is in high impedance state. So it should follow whatever it's connected to. And the brunt of our code is really just within this loop. We are setting the level of the LED pin to match the level of the input pin, very simply. So the header I've exposed exposes these functions. There's also a toggle function that's exposed here, which we may use later, but not likely. I type define an enumeration. So again, an enumeration is just a list of values that are associated. That's probably clearer now. It is a list of values that are associated. So I've listed out each of the pins that are exposed, and the value that's stored in this enumeration should match the underlying index of the pin in hardware. Likewise, I've defined an enumeration for a pin direction. So in order of inclusion, that's the pin direction input should have a value of 0, and output should have a value of 1, which should match the bit state in the registers to set. And when it comes to implementation, so if we set the direction of the pin, we are first checking to make sure the parameters that we pass in are valid. We then identify the port number of the pin that we've connected to. So if we recall, the port number is the number of the collection of 8 pins that this pin belongs to. So on the Atmega 328P, we have ports A through D. So when we set the direction of the pin, we have to access the data direction register for a specific port. So this DDRB evaluates to the memory address of the memory mapped hardware register we're trying to access. So in this case, it's just DDR for port B. So when we identify the port that's associated with our pin, we can use a switch case tree. So this is just a conditional evaluation based on this port number to identify which register to access. And unfortunately, due to the way that AVR libc in AVR io.h defines DDRB, it's not a straight up memory address, it's a dereferenced memory address that we're actually accessing. And I can show you guys that real quick. So from AVR io.h, we're including this IO, where's it, 328p file. So this defines all of the hardware registers as a helpful little technique. So we have our definition for oops, I clicked on the wrong one, 328p. Yeah, so we have definitions for, these should look familiar, the pin B, DDRB, and port B registers. This SFR IO8 is another pound-defined macro, and it equates to SFR IO8, where's that? Here we go. So we are defining this macro to mean it is a memory byte at this address plus some offset. And that is another pound-defined macro that equates to this. So at the memory address we provide via the macro, we are treating this as if it is a pointer to an 8-bit value in memory somewhere. And it's declared volatile because this is a hardware register that can change its value due to hardware changes under the hood. So we're casting this memory address to a pointer. Sorry, we are casting the value that we pass to this macro as a memory address, and then we are dereferencing that address. So when I say pin B or DDRB, we are taking memory address 4, so hex 4, and saying, sorry, we are taking value hex 4 and saying that's a memory address, and we're going to dereference whatever is at that memory address. So when I say bit update here, what I'm doing is accessing DDRB and doing some operation with it. So this pin num to port num and bit update are also pound-defined macros that I've provided. So to understand what bit update is doing, it takes the value defined by our destination. So in this case, it is a dereferenced memory address to DDRB. And then it's trying to access the bit at index denoted by bit. So here we are trying to access the bit associated with our pin. And we are trying to set it to the value denoted by our pin direction. So within our macro, we have the value that we're attempting to set bit at position bit in destination 2. In order to do so, we check if the value that we're trying to assign, so this logic level, if that's true or false, and I'm using the ternary operator to do so. So you guys may recognize that from the C lecture. But what this is evaluating to is if this value is high, then we set the bit. And if the value is low, so the alternate case, we clear the bit or we assign it a value of 0. How we do so is by the or equals bitwise operation here. So this is a bitwise assignment of the or of destination and this, whatever this expression evaluates to. So bit value evaluates to 1 shifted by the bit position. So if we shift left, we have our 8. Okay, so we're defining a value of 1, which for a single byte looks like this. And we are shifting it by our bit index. So let's say our pin is at index 3. When we perform our shift, we'll shift over by 3 positions. So we'll get this value. And then we're doing the bitwise OR of this value with our destination register. So in effect, if we're doing that OR, then all of these zeros do not affect the state of the register, but this one ensures that this bit position is set in our register. So that's what these macros are evaluating too. And when we do a clear, we do exactly the same thing. We set up a value via bit shifts. Then we negate it with the bitwise not operation. So that'll give us this. And then we perform a bitwise AND assignment with our hardware register. So that will say that when we're doing our bitwise AND, any bit that is 1 in both the existing register value and the value we're trying to compare to, if both bit positions are 1, then the value is still 1. If the destination register has a value of 0 in some of these positions, the AND will return 0. So we are not changing our register value in that case. And here, since we've set a 0 in this value that we're comparing to, so at the position that we want to clear, when we do the AND, even if the existing register's value has a 1 in this position, the register's value will then be assigned to 0 because the AND will evaluate 0 for this bit. So that's how we clear a bit within the register. And then this bit update macro that I'm using in our driver really just conditionally performs either setting the bit or clearing the bit based on the input value. And then I have some extra macros, pin num to port num and pin to pin index that are just helpful ways for us to take one of these enumerated pin values and turn that into the equivalent index in the port and the port that's associated with it. So that helps us identify which of these data direction registers to access and the index within that register to set or clear in order to set the direction for our associated pin. Let's see. So this is an example of providing simple utilities via C macros. Generally, I only assign macros to things that are small in functions because these macros are going to be copied by text directly into our code. So because these are pretty short operations, they don't take many instructions, so I think it's okay to define macros for them. But if you have a pretty big function or a pretty big chain of commands, then I would recommend instead dedicating a function to it. So an example of some utilities, and then an example of a driver for GPIO. So using those utilities, we can set the direction by setting the data direction register. We can toggle by writing via bit set to our pin register for the associated port at the pin index. We can get the level by reading from the pin register. And we can set the level by updating the port register. So hopefully this should all make sense now. So I'm going to go ahead and from our project directory, and if you guys have the repository downloaded, you can follow along with this at this point. So you would either open a terminal in this directory or git bash on Windows. I'm going to make to build our program, which should produce all of our build artifacts. And then I'm going to make a program with our, and then before you do so, you'll have to make sure that your make file is pointing to the correct COM port. So again, when we were setting our AVR dude, where is that? There we go. So if you search AVR dude port in the make file, just make sure you set that to the port that your Arduino is connected to. So I'll leave that up. So then we can run make program after we've produced our result files. Our device gets programmed, and now we can test this by, again, connecting our jumper cable from the VCC labeled pin, or I think Arduino calls it 5V. So that's our 5-volt pin. And that is equivalently a logic high. And we plug the other end of the jumper into pin 12. And we should immediately see the pin for the LED, set the LED on. And if you want to turn the LED back off, just connect to the ground pin. So again, this is just a demonstration that we can do basic GPIO functions. So we can control the state of a pin and read the state of a pin. So when I actually provide the application logic, we'll be using this driver to access each of the buttons. And it looks like we're already over time by a few minutes, so I'm going to call it there, and that's where we will get to with drivers. So I know today was a bit of a whirlwind, and there may have been issues with installation, so that's always a pain. If you guys want to stay on so that I can help you with installation, now that I've gotten through the material, I can do so. But if you have any questions related to the driver development or the build process, the upload process, those would be great questions to ask now. So Cameron, you raised your hand. You want to go ahead and ask?
Sorry, where was the documentation? I apologize. I was stuck on the download and then I got whooshed behind.
Yeah, no problem. So in the top level repository that you downloaded, there should be this docs directory.
No, not that. Sorry, where did you get the repository from?
Oh,
like where's
yeah.
it available?
Yeah, sorry. I sent it as a link via the group chat. I'm going to put it in the notes when I next upload. So that is the, yeah, that's the GitHub repository where you can download all of it. And it should look like this. So you'll just go to this button over here and hit download zip. Or if you have Git, then you can use Git to take it, but I'm assuming that no one knows what Git is right now. So yeah, any other questions on the tooling, how to interface with the make system, on the driver itself?
I have a question about the bittools.h
Yeah,
header file that you made.
I had a feeling it would be a bit confusing.
Yeah, so with that, I was under the impression that the defines are really just kind of text expanding macros.
Mm-hmm.
But I guess what you're doing is like you're actually passing arguments into these, and those arguments also kind of.
Yeah, so we are looking at these as if they're functions, but really any define is just doing text substitution. So if I were to say, I wouldn't do this in this file, but just as an example. So if I were to say like int a is bit val 5, this would equate to at compile time int a equals 1 shift by 5. So this is still doing a text substitution. It is just substituting with some additional text that you're passing to the substitution. So here we're passing 5 to the substitution. And so for this argument, we're substituting into the text that we're going to place into our file.
Okay,
so this still is not a function.
Yeah, I was going to ask, so why not make these as functions? Because I've done like the bit set clear, that sort of thing, but I remember doing them as functions.
Yeah, you can do it that way, and I originally did. However, generally it's faster to do something like this when it comes to implementation because you're writing, it's the equivalent of writing out this command directly in place where you use this macro. Whereas if you were to make this a function call, if you were to do something like, let's say, set that has to return empty. So I'm assuming that this bit set function is going to give us a value in 1 byte, and it'll be our position will be indicated by this parameter. So if I return cast UIDT, and I do this bit shift here, so this will require us to do a function call in as one of our machine code instructions. So we'll have to do a function call. We'll have to create that stack frame for this function, and then we'll have to evaluate the command within the function, return that value, and then assign that return somewhere. So that's already more commands
Additional.
and more processing time to do this bit set. However, if we do the macro instead, because of this direct substitution, we only have to do the command part.
Right, and for clarity,
time.
for clarity, I'm guessing on line 28 when you said bit set, you mean bit val, or get bit or something like that.
Oh yeah, sorry.
Okay, cool.
Yeah, that's totally just bit val.
Mhm.
So yeah, this bit val function is equivalent to this macro in what it will do at the end of the day, but how it gets there is actually slower if you were to make it a function. It is definitely cleaner to use functions, and because macros get confusing to look at if you don't know how they expand, I wouldn't normally recommend this for, like I said, complicated functions. In that case, I would use a dedicated C function to do so. But this is mainly for performance. Even though we don't need it, I wanted to show you guys how to do it.
Gotcha, cool.
Yeah, so if I didn't use these macros, I'd basically have equivalent functions defined in this gpio.c file. Yep. Okay. Sean, you raised your hand.
Yeah, so I have my Arduino hooked up to the USB port on my Mac, and I ran that ls/dev/dty.star, and all that shows up is a Bluetooth port, a .sock, and a .mals. So
Interesting.
yeah, I'm just not sure like why it wouldn't appear as a serial port.
Do you also have the Arduino IDE installed?
Yes.
Okay, so another way, and probably the easiest way to check the serial port is just to go into the Arduino IDE, do tools, and then look at the port. If the Arduino doesn't show up there, then I'm not actually sure why your Mac isn't seeing the Arduino. I would try a different USB port in that case.
Oh yeah, I'll try that.
Okay, but this should show you the serial port identifier that you can use in the AVRDude commands as well.
Right. No, it's not seeing it still.
So when you plug your Arduino into your computer, is your power LED on? So that should be a green LED on the right-hand side of your Arduino.
It is. It is on.
I'm wondering if your Mac just has like USB permissions for serial turned off.
Actually, I have another Arduino that I have been using. I just wanted to try using the one that came with the kit that you recommended. So if I hook that one up real quick.
You could also try another USB port.
Yeah, I tried a few different USB ports and it didn't show up. Oh yeah. Yeah, it works with this Arduino. I guess I'll just go ahead like this.
That is strange. I guess the one that came with the kit is bad then, unfortunately. Sorry.
Oh well.
You try swapping
Also,
out the cable next. Sometimes it's the really silly things.
yeah, if there's any pin headers on there, make sure that those are connected the way that they should be.
I don't think the Arduino has any default
I don't think it
header
does
jumpers.
either, especially from the kit, but
Let's see. Yeah, okay. So any other questions about the C code that we're using to drive this GPIO demo project? Because there's probably more stuff that's confusing about it.
If we don't have questions at this time, can we email you?
Oh yeah, yeah. And
Okay.
next workshop, I'm going to be finishing all of this up, and we will likely have some time at the end to talk about it as well. I do want to give you guys some time to like percolate and sift through the code yourselves, do this full programming cycle, and then if things don't make sense afterwards, or like if you make a modification and see what it does. If things don't make sense after that, by all means, ask questions next time. I am also available if you're on the AES Slack.
Yeah, I was gonna say if you do have questions, rather than emailing, go with Slack first. Just because 2 reasons, I guess. One, Michael is pretty active on there. That's actually primarily how I communicate with him throughout the week. But also that way, if you have a question and someone else has that same question, hopefully, we can kind of get it answered there, or sometimes other people have already gone through it and they can jump in and tell you what to do. So, that's what like the general channel would be for, or yeah, just like post your stuff there, and it's all relevant to what we're doing. So definitely on topic.
And if you're not on the AES Slack, I am available via email, and we'll post that. There you go. So yeah, if you have questions and for some reason you can't reach me via Slack, you can email me there, and that's totally fine.
Actually, I do have one more question.
Mhm.
So now that I've found with this other Arduino, I found that the port I want is /dev/cu.usb modem 14501, and then that's a little bit different than COM3. Should I put that whole thing in for COM3?
Yeah, that's probably your serial port identifier. If that doesn't work, well, is that actually what shows up in Arduino?
Yes.
Okay, then yeah, that's your entire serial port identifier.
Okay.
So that
cool.
would be in any of the make files that you're going to be using to talk to. Just make sure you modify this line that contains AVR dude port so that it doesn't say COM3 and instead says your serial identifier. And likewise, if you're going to do the bear commands, that -P, like capital P, would also take this that serial identifier.
Okay. And then all I have to do is get into the repository and run the make.
Yeah. So if you inspect the make file, the 3 targets that you can run are make or make all. Those are equivalent. Make clean, which clears out all of the build artifacts that are produced when just doing make all. And then make program. And make program will upload to your Arduino, assuming it's plugged into the port that you specify using AVR dude.
Okay.
And if you look back in the video after it's posted tonight or the lecture notes, this process should be detailed in instructions in there. I'm pretty sure I'd left a bunch of tutorials in there as well for like how to do this generically.
Okay.
But I wanted to give you guys some live demos of it today so that it's not completely foreign when you guys start playing around with the code. And yeah, you guys are clear to use this makefile for other projects as well. Specifically, if it uses like AVR chips, this won't work for any other architecture. So like if you have an ARM controller, like some Arduinos use the AVR instruction set, the ARM instruction set, and that will not be compatible with this toolchain or this makefile. But if you wanted to target a different microcontroller, all you have to do is modify the variables in this file for the correct microcontroller frequency, and then like if you make subdirectories, you just need to include that in the source directories variable here.
Okay. So I made the I ran make, and it started, but then it said bad CPU type in executable. Error 126.
That's what's happening with mine too.
Okay, you guys are all on Mac, huh?
Yeah, I'm on Mac too, having the same issue.
Okay, did you download CrossTools?
Crosspack, yeah.
Or CrossPack,
Yeah.
that's it. Okay, it's possible that that project is broken. I am really sorry for all the Mac issues. I guess people don't usually do microcontroller development on Mac. Bash AVR dude command not found. Okay, that sounds like a different issue. Wait, are all of you guys on Mac?
That's not Mac. I mean, that's Windows.
Gotcha. Okay. I suspect that the Mac issue with Make is with Crosspack. I think that was what it was called. I'm not sure if there's an alternative. You can manually grab AVR libcc, GCC AVR, and AVR dude offline. And I'm certain if you Google it, there will be a pretty easy way to find it. But I don't have those instructions pre-prepared for you guys. Sorry about that. I'm really surprised that Crosspack isn't working though. Like, yeah, if you were following these instructions, it should work out the box, unless Crosspack is now just not supported anymore. But yeah, the bare AVR libraries and tooling should also be available generically if you Google search for them. Yeah, AVR8 GNU toolchain is exactly what you're looking for. There may be some fiddling with your environment variables to make sure that the tooling is all on the correct path. And that's what I was hoping to avoid with these different install instructions. In practice, it'll look a lot closer to the Windows instructions if you are going to install manually. It won't be identical though. Let's see. What was the other issue? AVR dude command not found. Okay, so if AVR dude command not found and you're running on Windows, then I would suspect that your environment variables haven't been set correctly. So on Windows, I'm going to just search environment variables, click on the environment variables button here. Go to path and edit the path. And if you downloaded AVR dude and dumped it into C program files, then I would set that as one of our path environment variables. And then I can confirm that it exists on my machine at least. Let's see. Program files, AVR dude. And then the AVR dude executable should be available directly in that folder. Okay, so it doesn't work from, oh, wait a minute. Are you running via command or git bash? That's really weird. You're certain you set path?
I can just share my screen on my PC.
Yeah, that'll work. I should probably stop recording, huh?